Hello everyone, welcome to this tutorial on ROBOKINE, a free Python-based software platform for robot kinematics, workspace analysis, trajectory planning, singularity evaluation, and machine learning-based inverse kinematics. In this video, I'm going to walk you through the complete workflow of ROBOKINE, from configuring a robot to generating trajectories and exporting your results. Let's get started. Okay, so first we're going to start off with robot configuration. When you first launch ROBOKINE, you're going to see the main interface divided into several functional modules. So we're going to start with the robot setup panel over here. So the example that we're going to be going through is going to mimic the first case study from the research paper that outlines what the software is used for. So we're going to start off with 4 degrees of freedom, which is the case study for the first one. And then we're also going to update these joint types over here. So here you're able to configure each joint individually, and you're also able to change the motion axis, change the link length, change the home position whenever you want to reset it back to where you started, and also the minimum and maximum of the axis of rotation as well. So before I change any of these values, I also want to point out that there are multiple different presets down here if you don't want to mess with all of these very specific values and things that you have to change. So I'm going to kind of go through a little bit of clicking this. So this first one is the serial arm. You also have where you can kind of see that it all gets updated based off of what it says right here. And you have the Scar-like one where here you get 3 revolutes and 1 prismatic, and then you have all the motion links as well. And then you can also change these sliders, and you can see how quickly everything just updates right next to this in the 3D, like the 3D configuration panel as well. So it's very user-friendly and easy to use. And then you also have the Cartesian robot. You also have the cylindrical robot. You guys can play around with that more on your own, but I'm going to talk a little bit more about the case study one. So as you all might know if you read the paper, the first case study from the paper is built off of a 4 degrees of freedom RRRP robot. So that means that there's 3 first revolute joints. So I'm going to change all of these to revolute. And then the last one is a prismatic joint. So I can quickly change that to make this easier to just mimic on the software. And then I'm also going to change these axes just to make it easier for us to work with. So we're going to do plus Z on the top, plus Y again, and then a plus X on the bottom. So this is easier just to like move along here. And obviously these link lengths work, but I'm going to make them all 100 for ease of use. And you can see how quickly it just updates on the right side as I change these numbers. And you're also able to see that the overall environment here is changing and increasing to allow for the entire workspace to be used. So now that we have all of this configured, we change the motion axis, we change the link, and we change the joint type. We're actually going to start working with how to actually calculate the forward and inverse kinematics, trajectory planning, and all the other stuff and cool features that are on here too. Yeah, so let's move on a little bit too. So just to make sure you guys know, the joint presets are here, and then we also have the easy configuration right over here. If I ever do move these sliders and I want to get back to the original position, I can always just click go to home position right here, and then that'll take me right back. And if you'd like to, you can change the home position quickly by setting the current sliders and where their position are to home. And then you can also reset home and go back to the original home position and set all the sliders to 0 once again, which is usually the general home position. All right, let's move into forward and inverse kinematics as well. So there's 2 more modules down here where you can see. First is the inverse kinematics over here, and you can also see the forward kinematics in this area too, and also the joint configurations. So forward kinematics is always going to update whenever a joint value is changed. So as the sliders move, ROBOKINE continuously computes the end effector position and updates the transformation matrix and the numerical output panel. So this is right over here. This is the whole numerical output panel that'll give you the inverse kinematics solved from whatever value points you put in, whatever targets you put in, and it kind of just lets you keep track of all the numbers and joint configurations throughout. So what we're going to do now is we're going to test this inverse kinematics target. So here you can kind of see that there's already some preset numbers in here. For target X, it's 180, for target Y, it's 60, and for target Z, it's 120. So I'm going to try to get the robot to move to this position here, and you can see that it actually does. And that means that the position that the robot in isn't actually singular. So you don't really get an error here, but I'm going to try to get an error just for learning purposes and so you guys can understand how you can actually use the software. Let's do 10 right here and 20. See if that does that work. All right, so I'm going to solve IK and robot. Oh, that worked. So let's do 1. So that's okay. I'm I'm gonna do 10 here. Yeah, so that part didn't work. So now you can kind of see the target could not be found, and the final error between like the closest position it could get to was around 35, which means that it's not good enough and that the robot would have been in a singular position if it actually tried to go to that target. So that means that we can't really use these positions. I'm gonna use one of preset position that I know is gonna work as well to kind of just show you if I choose to adjust this, how it quickly it'll update. So let's do 160. Negative 314. And we're gonna do negative 185. So this is a pretty simple position, but you can kind of see how this is already in this like convoluted position over here. But if I solve the inverse kinematics, oh, actually, this does not work. Well, I'm gonna change this a little bit, but let's do 180. Or no, I guess not. But I'm gonna reset back to what it was before, and we can go back to that position since it worked. So this is what you can kind of see here when it works. But here, we can see here is the end effector position is located right here. And whenever I click solve inverse kinematics and move robot, you can see all of this solve the specific position it's trying to go to. And it shows you the error of where it could actually get to compared to the target position, and also the angles of each joint. So right now we have 4 joints because there's 4 degrees of freedom. So that all is calculated right here, and that lets you understand like the mobility of the robot as well too. All right, let's move on a little bit and start talking about the workspace generation and singularity analysis. There's some pretty cool analysis tools down here. If I scroll down, you can see workspace generation and singularity checking, which are your main areas to actually do this. So through this, we're going to be able to examine the robot's reachable workspace. So by clicking generate workspace, you're going to see ROBOKINE automatically randomly sample valid joint configurations and display every reachable end effector position. So I have 3,000 workspace samples right now. So if I click generate workspace, you're going to get this kind of cloud system right here where you can see exactly where the robot can move based on its current configurations too. So this is pretty cool. And you can also make sure that if you're trying to get to a point around here, you're probably not going to be able to do it, and you're probably going to get an error, which is exactly why we had those problems when I was trying to enter values in up here. So you can kind of see that too as well. But yeah, and let's move forward a little bit. And then also with singularity checking, something that you can do is ROBOKINE will be able to calculate the several important metrics in a part of the singularity checking aspect, which is the Jacobian rank, the manipulability index, singular values, and condition number. So I'm just going to click check singularity right here. And it says regular, not singular for translational position tasks, which means the position that it is in doesn't actually make it lose a degree of freedom or anything like that too, which is good, and make sure that our robot is actually able to move from this position as well. All right, now we're going to move into trajectory planning and how you can actually do that with the robot here. So the first way you actually start doing that is to generate your via points to see like how the robot moves between different points that you pick. So you can obviously, if you scroll up here, this is the via point selection section. So you can always add via points from the fields that you enter in right here. But what you definitely want to do is kind of just use the sliders up here to come to your via points. It's a little easier, especially for me, because you don't have to keep guessing whether it's a singular point, the robot will get into a singular configuration, or it can't be reached because it's outside of the workspace. So I'm going to move this back into home position. That's where we're going to start off. It's going to be the original starting point when we do this trajectory planning aspect. But I'm going to move the robot around kind of just randomly to see where we can end up. So let's do this as our first via point. I'll give you even more. I'm actually going to change this to positive x over here. It's a little bit easier to use. That's going to be our first via point. So after I move the sliders here, I'm going to say add current end effector as via point, and you can see that show up here as 0.1. I'm just going to keep doing this. See, let's go over and then turn them here. Maybe come back a little down and then raise that up. So that's going to be our second via point. So I'm going to scroll down over here. Add that as a second via point. We're going to do one more. maybe here too. So that's where that would be. I'm gonna add, this is our last bio point right here. So now we're gonna get into this trajectory planning section before we actually start the animation. So I'm gonna use fifth order polynomial because that's gonna be the best one just to ensure smoothness and less jerk. And you can also really see how the acceleration starts and ends at 0, which allows for that smoothness and lack of jerk. So here you can also change the segment time, samples per segment, and animation delay in milliseconds. I'm not really going to touch that since we're kind of just showing a demo here. Okay, we're back. I just made some adjustments to the via points, and now we are ready to start the trajectory planning. Like I was saying, whenever you have all these via points down here, you can click solve IK for via points, which is just going to solve the inverse kinematics, and you get all of these values right here, which show you the error from where it's actually supposed to go for each point, and also the angles of each joint just to get to that specific point too, and also where it's moving to. So now what we can do is we can click generate trajectory, and this is going to show you the path of how it's going to get to all these different places. And now I'm going to keep fifth order polynomial, and then we're going to start off by clicking start fast animation. And then the trajectory planning graphs are automatically generated over here. So you get joint displacement, joint velocity, and joint acceleration. And you can see that the robot's actually moving around here, going from home position to point 1 to point 2. We can just watch that. These plots are especially useful for just understanding the motion smoothness and also comparing the trajectory planning algorithms. So you don't just have to stick with fifth order polynomial for each bio point you do. You can switch between linear, you can switch between parabolic blend. There's a lot of options just to test things out without having to do it physically. So that's kind of the entire animation over here. Now that we're done, I'm going to click stop animation. So here you can open up all the graphs. You can see the trajectory planning graphs over here. You can open them up separately here too. You can open up all of them together, maybe save as a PNG right over here. So now the biggest thing is we're going to try to export the results over here. So I'm going to save this animation as a GIF. So let's do get tutorial. So that's going to be the main one that we do here. And then what I can do is after I get the notification that it's already saved, I can open up my Finder and open that and we can watch it as a GIF. And that's going to be a lot faster than what's being seen here too. So let's open this up. And you can see Get Tutorials 3. So this is kind of what you can see if you click on the Get Tutorial 3.gif. And then you can see it going from home position to point 1 to point 2 to point 3. And it's a little bit faster than the actual one that we saw when it was calculating it here. But yeah. And then finally, ROBOKINE also has another extension module called the Machine Learning Inverse Kinematics module. So this interface allows users to train and compare the random forest, KNNN, or K nearest neighbors and neural network models using forward kinematics generated datasets. So I'm going to kind of close this one over here. And you can see this as a new GUI. But once trained, these models can rapidly predict the joint configurations for new end-effector targets. So this is pretty similar to the old one with the RoboGeometry and joint limits and degrees and the ROBOKINE one. So I'm going to kind of talk about this right here. So you can change the model type right here. So let's start with random forest. So I'm going to train the inverse kinematics module after I click generate forward kinematics data set. So this is going to all come up here. Then I'm going to train the ML inverse kinematics model. This one's really quick, so you can kind of see that this comes up with a 269.22 millimeter mean Cartesian error. So that's pretty good. Could be better. So we're going to go to the KNN, train the new machine learning inverse kinematics model. And as you can see here, this is a different model outcome as well. And the mean Cartesian error here is around 242, so a little bit better. And that's pretty quick too. So the neural networks is the last one, and this takes a long time to generate, so we're not going to see it in this tutorial video. But you can train the machine learning inverse kinematics model here. That's going to take some time, but as you can also see up here, that gives you the joint prediction error and error in degrees for each model. So this is kind of getting better as you move down the machine learning models too. But yeah, so there's a lot of different options for what you can experiment with. So this makes RoboKine an excellent platform for both the traditional robotics education and also modern data-driven robotics research, especially within ML. It also shows that both machine learning inverse kinematics and also numerical inverse kinematics can be pretty well incorporated together. So thank you for watching this tutorial. To learn more, explore the full documentation, example projects, and research paper available in the RoboKine GitHub repository. Thank you.